Okay, so EE431 satellite communications is a module that we are discussing on. So in the last class, we discussed about the main components in a satellite communication system, right? Main components. So basically, we have satellites, satellites that we'll be considering, and they will be orbiting in specific orbits around the Earth. So there's a specific orbit that they need to follow when they are orbiting around the Earth. Secondly, we have the ground stations. The ground stations that lie on the ground or lie on the surface of the Earth. So basically, we can define. I mean, we have defined, like ground stations on the Earth. So I think in this simulation, we cannot, we haven't specified the Earth locations. However, like we can define the locations of the ground stations on the Earth, and we can communicate with the satellite. We can establish the communication link with the satellite from those ground stations. And then we have the communication link. Yeah, so basically we discussed about those three components in the last class. So I will continue to discuss about these three components further as well. So when we talk about the when we talk about like satellite communication scenarios, we need to follow specific frequencies for transmission and specific angles of transmission and specific transmission powers. So likewise, we need to specify the transmission signal transmission power, signal transmission frequency, signal transmission angle. We need to specify parameters such as frequency, right? Transmission. We need to, in order for us to achieve satellite communications, we need to follow certain standard frequencies and communications, so on and so on. So let's discuss a little bit about that, right? So to achieve like proper satellite communications, between the transmitter and the receiver. It could be the transmitting device could be the ground station, and the receiving device or the equipment could be the satellite. So in order to achieve proper satellite communication between the transmitting device and the satellite, then we need to maintain some specific transmission parameters. So we need to maintain transmission parameters such as frequency, right? Frequency of transmission, um, angle of transmission, right? Angle of transmission, angle, I will say. Then angle, and then also the transmission power. So mainly these three factors we can consider when we are transmitting signals and when we want to achieve satellite communications. Okay, so as you can see now, like in this simulation, of course, we cannot directly see how the ground station and where the ground stations are located. So let me try to get that visualization as well. Okay, so I think this is great. So in here we have a situation where we have a ground station in our like location. Like in here we have, in India we have a ground station. Okay, so and then we have uh, basically a satellite orbit which is going around the Earth. So I think I need to zoom it in to obtain the like entire Earth view. Okay, so however, like for the moment, I think we can observe both the satellite and the ground station. I will try to get a zoomed out view of this. Yeah. Oh, so this scenario depicts a scenario that has two satellites out in the orbits, and we have one ground station here in an area near the Indian subcontinent, and then we have another ground station in the area which is in Australia. So in this situation, we want to communicate between these 2 points. We want to communicate between this Indian continent point and the Australian continent point. So what we do here is we use satellite communication to send a signal to the satellite in this orbit and in this first orbit, and then that satellite communicates directly with the other satellite in the other orbit, the second orbit. So once the second orbit has the information, it transmits it back to the Australian continent and to the ground station there, right? So in order for us to achieve this communication, we need to, send the transmitting signal from this ground station towards the satellite, right? So achieving that requires, as I said before, the correct frequency, the angle, power. Apart from that, we also need a line of sight, connectivity between I'm sorry, I think I have lost the connection in between where I was explaining the concepts. Hopefully now I think we'll be able to obtain the monitor again. So I was explaining about the situation of obtaining satellite communication link. I mean, like generating a satellite communication link between the ground station and the satellite. Okay, so like there's a ground station on the Earth, and we want to communicate with the satellite in the orbit. So we have to consider transmission parameters such as the frequency, angle, power, uh, uh, to communicate and to transmit the signal reliably and properly to the satellite. Apart from that, we also need to maintain line of sight connectivity with the satellite out in the orbit. So normally, in normal communications that we do in the around, I mean, in the Earth, like between like two, maybe two devices, we don't use satellite communication mainly because we do not have the line of sight connectivity, right? So in our normal day to day like communication between like two devices which can occur uh, between, I mean, two devices, I mean, across a certain network infrastructure. So once we are communicating, there are so many like obstacles in that path that we are sending the signal through. So once our signal is hitting obstacles, it loses the line of sight connectivity, and it uses multipath fading phenomena and reflection and such kind of effects to send the signal to the end destination. So in that case, the signal goes through a lot of obstacles. However, like in satellite communication, we cannot achieve communication with the satellite properly if we have obstacles like that. So we need to have line of sight connectivity with the satellite that is out in the space, right? So I think you have seen like there are many satellite dishes at even at SLTC. So all these satellite dishes are totally rotated into the outer space, and the satellite dish is directed towards the outer space such that those satellites are, I mean, directed out into the space because in in that uh, that manner, the satellite communication or the satellite signal can be can be sent directly to the satellite, and we can achieve line of sight connectivity with the satellite. So so basically, when we are working with satellites, we need to make line of sight connectivity with the satellite. So in I think in SLTC we can see huge satellites that were in place and used in the past. So I think we will discuss about the situation of satellites uh, currently at SLTC in a later time. However, now we will discuss about the um, like the phenomena of like generating the correct satellite signals to communicate with the uh, satellite out in the space. So as I mentioned, if we use the correct frequency, angle, and power, we will be able to achieve the satellite communication, the proper satellite communication with the satellite. However, if we don't have such kind of you know transmission parameters properly, uh, you know properly calculated and properly used, then the satellite signal or the signal that we want to send to the satellite will get reflected back uh, across the um, like atmospheric levels that we have in the atmosphere, right? So once we are sending signals using our satellite dish, right? So we have a certain like equipment in here which we call as the feed horn, right? So once we generate a certain signal at the ground station, we you know we send it through this feed horn into the satellite dish. So once the satellite dish reflects it in a certain angle, it will be sent to the space in a certain direction. So once we are sending the wave up into this space, um, the signal is going through multiple atmospheric layers. So there is a mainly there's one layer which is having uh, a um, dense concentration of ionized charged particles, which we call as the ionosphere. So in the ionosphere, we have a high concentration of ionized charged particles. Okay, we have a high concentration of ionized charged particles, right? So in this situation, we now we face the difficulty of sending our signal to the satellite in a proper manner. The reason is since the density of this ionosphere is very high, the signal that we send to the ionosphere gets reflected back and comes back to the earth in another angle, right? So because of this phenomena, the signal that we send, if we do not send it in the correct angle, the signal will bend and will reach a different location than the location that we intended to send it. So the signal will not reach the expected destination. It will go somewhere else. So because of that, we uh, we we uh, we face this total internal reflection situation. If we have this uh, if we have send the signal using a wrong angle up into the space. So we need to consider this total internal reflections scenario when we are sending the signal out into the space. We need to calculate what is the critical angle that we have to avoid, and we need to send the signal in an angle which is lower than the critical angle. If we send the signal in an angle which is more than or equal to the critical angle, the signal will reach the total internal reflection scenario, and it will get reflected back to the earth in a different direction of propagation, and therefore the destination will not be reached. The destination that we wanted to reach will not be reached. So because of that, we need to maintain the correct angle when we are transmitting the signal. So that angle will be controlled at this location where we send the signal at the satellite dish. So that will be controlled again by the feed horn, and the angle at which the feed horn is transmitting the signal to the satellite dish. So that signal transmission part has to be correctly done in order to send the signal in the correct angle to the satellite dish and thereby to the space. So basically that is regarding the maintaining the correct angle when transmitting the signal. Apart from that, we also need to maintain the correct frequency, and basically in for satellite communications we have a specific frequency that we are using. So that frequency we need to use to maintain the satellite communication in a like a reliable manner without much um, much loss in the signal. So we will discuss about the specific frequency bands that are used in the satellite communication in a little while. So we will basically discuss also about the applications of the satellite communications. right? Applications of the satellite communication basically will be focused on providing communication between two distance points on the earth, right? So satellite communications are basically used for communication between two distant points on the earth, right? Two distant points on the earth, points on earth. So we can see in this simulation that we have two distant points on earth, which are, one is located in the Indian subcontinent, other one is located in the Australian continent. So when we want to communicate between these 2 points, we can use either fiber. I mean, if you are using other means, we can use the fiber communication links. So apart from that, we can use the satellite communication links. So, so using satellite communication links means having the satellites out in the orbit. So, like there's a advantage of using satellite communications in situations where we cannot reach the other location using fiber connection. And therefore, satellite communication help us to communicate between 2 points which are which are distant, very distant apart, right? So we are talking about communication that happens between countries around the earth. And also the communication is satellite communication is useful for GPS navigation purposes. GPS navigation purposes, right? So we will talk about GPS as well. So GPS relies mostly on the satellite communications, and with the presence of satellites, the GPS location is calculated. So uh, we require the existence of these satellites for the GPS location to be calculated. Apart from that, satellite communication will be used for weather forecasting applications as well. So, since the satellites are held in an orbit around the Earth, it is able to observe the changes that happen in the atmospheric level and in the space. And therefore, it can predict the situation of the weather that can occur in the upcoming days and forecast the weather. So, these kind of applications uh, are the useful applications of satellite communications, right? So, Uh, now let's discuss about the satellite itself and the activities that happen in the satellite, right? Or else, I mean, we can talk about the ground station first as well. So I will discuss about the ground station first. So the processes that happen in the ground station we can discuss, right? So in the ground station, we will have both the receiving function and transmitting function, right? So let's consider a scenario where we are uh, you know transmitting the signal using a satellite dish towards the outer space, and we have a certain feed horn in here which is used to transmit the signals to the satellite dish. So as I said before, after sending the signal to the satellite dish in the correct angle, the signal will be propagated out into the space in the correct angle that will go through the ionosphere as well. And you know it, I mean, it will not be affected from the ionosphere effects. And since the frequency of this signal will be very high, it will be in the range of like 1 to 40 gigahertz. And since the frequency is really high, and its strength also is high in that scenario, it is able to penetrate through this ionosphere and reach the satellite correctly and properly in the space. So uh, the satellite will be receiving the signals that are sent from the ground station, and there are antennas placed at the satellite to receive the signals that are sent to it. There are many antennas that are placed in the satellite. So we have antennas separately for transmitting and receiving operations. So we have one antenna for receiving, one antenna for transmitting. Let's say there are only two antennas, but there are multiple antennas that are placed in the satellite so that it can transmit the signals in a certain direction with more convenience. I mean, more flexibility and more efficiency. So because a lot of customers are using the satellite services at one time, so we will use like multiple antennas at the satellite to cater multiple customers at the same time. So we will have multiple antennas at the satellite. So by doing that, we can cater multiple massive amounts of customers. So basically, at the satellite, we will be, like receiving the signals, processing the signals to a certain level, and then we'll be transmitting back to the receiving satellite dish. So a certain satellite dish will be receiving the signal at the ground. So we will have the other satellite dish placed at the ground like this, and we will have a feed horn to collect the signals that have been received by the space. This signal that has been transmitted from the space will be reached at the satellite dish, and it will be reflected to the feed horn. So the feed horn will collect that signal, will do the necessary processing over there. So we will talk about the processes at each location uh, in this system. So if we talk about the transmitting satellite dish, right? Transmitting satellite dish, there is a feed horn in here for this as well, and that feed horn is used to supply the signal to the satellite dish, and satellite dish will transmit the signal using reflection to the satellite. So the transmission part will be done in here, and the it will be transmitted in the uplink frequency. So there will be a separate uplink frequency for transmitting the signals. So let's say it's FU, let's say, and sorry, let's say F1 or something, F1, and then we will have a downlink frequency, which we call as F2. So the satellite, it will receive the signal that is sent to that satellite, and it will process the signal in a certain order. So when we take the process that is happening inside the satellite, we can draw a small block diagram to represent the process. Right. So I will have to erase this part, and then I will explain about that. Right. So basically, the in between part, that is between the RX antenna or the receiving antenna and the transmitting antenna, is known as the transponder, right? So if I draw the receiving antenna, and then we have a part called the transponder in here, transponder. right? Transponder, and then we have the transmitting antenna, which we will name as TX, right? So I think my drawing is, I will draw it again. So let's say like there's the receiving antenna. Let's say receiving antenna is here, and then we have the transponder, and then we have the transmitting antenna. Let's say it's TX. Let's say this is RX. At the transponder, all the necessary processing will be done, right? So let's like try to discuss that. So at the RX antenna, we will be receiving some signal, and that received signal will be sent to a component called low noise amplifier. Low noise amplifier. So low noise amplifier uh, will uh, will be used to amplify. Let's amplify the weak received signal. The weak received signal, right? So the low noise amplifier is used to amplify the weak received signal, right? So initially at the satellite, we will receive a weak signal. So we need to amplify the weak signal, and we use the low noise amplifier to amplify that signal, right? And then uh, what we do next is the amplifier section, right? So you will ask, why do we have another amplifier? So I will explain that in a little while. So we after the amplifier, after the second amplifier, we have the filter, and then we have the demodulator, demod, right? Demodulator, and then we can do some processing of the signal. If we want to do some processing, we do the processing. And then we do the modulation. Then we can do the amplification, right? We can do the amplification, and then we will do filtering again, and then we will transmit it to the space. So I will now explain the process one by one. So once we receive a signal from the Earth station, let's say like the Earth station in here, like from India, let's say, right? We receive the signal from India, and then we receive the signal at the receiving antenna of this satellite that is here in this orbit. And then the satellite will have a transponder which will include these components, right? So basically low noise amplifier, filter, a demodulator, processor, modulator, amplifier, filter, and again transmitter. Just after filtering, you will come to the transmitting antenna. So basically, the all the process between the receiving antenna and the transmitting antenna we will call as the transponder. So this transponder will do like these kind of steps. So first it will amplify the weak received signal. So at the satellite, it will receive a certain weak signal, right? The reason is that it is very far away from the Earth. And because of that, the amount of signal strength that is received is low, and we need to amplify it to a certain level in order to decode the information. And then in the amplifier stage, we amplify the uh, specific frequency components, right? We amplify only the specific frequency components. I will try to erase this, right? In the amplifier, we amplify specific frequency components, specific frequency components. So we know that our communication is done in a certain frequency range, and our signal is within a certain frequency range. So uh, if the satellite has the knowledge about the frequency range of the signal, then it is then using this amplifier to amplify the signals of the uh, of certain frequency components, right? It will select select the necessary frequency components that it needs to amplify, and then amplify that signal in that with those frequency components. After that, it will use a filter to filter out unnecessary signals, noises, interfering signals from the signal that it receives, right? And then after filtering, it will now use a demodulator to demodulate the signal. And after demodulating, in the processing stage, the information can be decoded if needed, and if it can do any adjustments to the information that it has received, and then it can then go to the next stage. So in the next stage, the we will be modulating the signal to a certain frequency range that is intended for the downlink communication, right? So since we are going to transmit now from the satellite to the ground station, we'll be using the downlink frequency. So we'll be using the downlink frequency as our carrier frequency, and we will be modulating the signal. And then we will have the amplifier to amplify the signal that we are going to transmit up to a certain transmission power level, such that it will be received very well at the ground station. And then also we will be filtering out unnecessary signal components from the transmitting signal, in order to make sure that we are sending a very high quality uninterfered noiseless signal. So once we have filtered the transmitting signal, we will be reducing the unwanted signals with unwanted frequency components, and then we will be having a clean signal. So that clean signal will be sent out by the transmitting antenna into the uh, into the space, and it will be directed to the ground station, right? So at the satellite level, it will process the data and it will transmit back to the ground station. So that is basically the process that is done at the satellite level, right? I hope it is okay, and you have if it's I hope it's clear. If you have any questions, please let me know. I will now erase this one. I will discuss about the hope you have no questions regarding this process. And now I will discuss about the receiving side of the signal. So as I explained before, we have communication done, or communication with the satellite, and now the satellite will transmit signals back to the ground station. So the satellite dish at the receiving location will be receiving the signal, and the process will be a certain process will be followed at the receiving location. So we have the satellite dish, right? We have the satellite dish, and we have the signal. We have the signal that is, hitting the satellite dish, and it will reflect back towards the to the feed horn, where the signal will be received. So the feed horn will be collecting the data. At the feed horn is like the equipment that is placed in the middle of the satellite dish, right, just above the satellite dish, to collect the signals that are reflected on the satellite dish, right? So the signal will be coming and hitting the satellite dish, and the reflected signal will be reached, will reach the feed horn, and the feed horn will do some processing of the signal, and it will send the signal to the receiving receiver, and a um, packet extraction which is done in the computer. So at the feed 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 point, we'll again draw this. So the feed horn will have the several components, right? We will have a band pass filter at the feed horn level, and a low noise um, amplifier, and a down converter, right? So at the feed horn, we will, after receiving the signal, we will send the signal through a band pass filter, and we will send the band pass filtered signal to a amplifier, low noise amplifier, and a down converter. Right? So the signal will be down converted to lower frequency, right? So the signal with the higher frequency will be cut down converted into lower frequency, and then that signal will be sent to the processing unit in the computer. So there will be a computer that will receive the signal and will do the packet extraction and decoding processes. Packet extraction and decoding. So the processing of the data that is received will be processed at the computer. After that, the data that is decoded can be used in our own devices, and we can reliably retrieve the data. So that is basically the functions that are happening in the receiving side of the satellite dish. Right, so I hope it was clear. So this is the satellite dish. It's hard to like get the shape of the satellite dish. However, like this is the best I will be doing, I think. So this is the satellite dish, right? So once you see the satellite dishes in SRTC, I think you can observe the components of the satellite, I mean, dishes and the grounds like station. Then you will be able to observe the feed horn, and you will be able to observe the like connection from the feed horn to a certain like processing unit at the back of the at the back of the satellite dish. We have like a box, right? We have a box at the like bottom of the satellite dish. We have a box where some processing will be done that we mentioned. So they'll be doing filtering of the signal and low noise amplifier functions. And then we will send that signal to a computer that is located in a certain rack inside the building, in our like processing a unit, right? In the building, we will have a certain processing room, and we will send our signal to that processing room. So the rest of the processes of signal decoding will be done in that location. So anyway, we can observe these components in our own SLTC premises. So that is basically regarding the functions that are happening at the satellite and at the ground station. Right, I hope it is clear. I will erase these. Now we will discuss about the frequency bands of the satellite communications, right? So the satellite communications cover a wide range of frequency bands between 1 to 40 gigahertz, right? So satellite com covers a wide range, of frequency, wide range of frequency bands ranging from 1 to 40 gigahertz, right? So therefore the satellite frequency range is known as this 1 to 40 gigahertz range. This is known as the satellite frequency range, right? And the satellite frequency range is further divided into several frequency bands, right? There are several frequency bands that are defined under the satellite frequency range, right? So those bands are known by different, letters: L band, S band, L band, S band, X band, C band. Likewise, there are bands: KU band, uh, KA band, then K band. Right? We will go into detail about these bands. So the satellite com bands will be L band, right? L band, S band, right? Uh, we have C band. Likewise, we have several bands. So we will try to categorize these bands by its frequency and its application. The L band is between the frequencies of 1 to 2 gigahertz, right? So any signal that we transmit between these two frequency ranges in the satellite communications we call as transmitting in the L band, right? So this is used basically in mobile communications, mobile satellite communications, right? Mobile satellite communications, right? Mobile satellite communications. So I will explain about that in a little while. I will first try to explain about all the bands, and then I will get into the applications of those bands in a little while, right? So L band, S band, C band, right? So we have the L, S, C, X, KU band, KA band, K band, right? So so this uh, these bands are like named basically depending on the application at for which they are used, right? So S band is used for applications such as mobile satellite communications and applications by the NASA, the deep space search, and so on. And then we have the communication range for S band between 2 to 4 gigahertz, and this band is used for mobile satellite communications, just as the L band, right? Apart from mobile satellite communications, it's used for NASA applications and deep space explorations. Deep space explorations. So, so for deep space explorations, this band is used. Then we have the C band. C band is from 4 to 8 gigahertz. Then that is used for fixed satellite services. Fixed satellite services. Fixed satellite services. Yes, fixed satellite services. I will discuss about that also. Uh, we have fixed satellite services for communications between fixed points on the earth. And then we have the military applications, and that one, right? That one we have from 8 to 12 gigahertz expand. Expand we have between 8 to 12 gigahertz. It's used for military meteorological purposes, right? Military meteorological purposes, right? So specifically for those purposes, these frequency ranges, these frequency bands are used. So these frequencies cannot be used for other applications. So that is the kind of standard. And then we have the KU band. In that band, we have the frequencies ranging from 12 to 18. And in that one, we have applications such as TV, radio broadcasting, those kind of applications. And in here, Yeah, in those in the KU band we are using this frequency range 12 to 18 to have TV and radio broadcast. And then we have communications under the band KA band. Sorry, K band. Right, sorry, it should be K band. K band is from 18 to 26. 18 to 26. It will do communications related to fixed service satellites. And then we have communications happening from 26 to 40, which will uh, focus on broadcast satellite systems. Broadcast satellite systems, right? Broadcast satellite systems. I mean satellite services. So likewise, that is one of the main, categorizations of the satellite communication bands. So these are the main satellite bands that are defined as of now. So these bands are like targeting, generated and allocated targeting a certain application scenario. So the depending on the application, the users will, I mean, the telecommunication service providers will use that specific frequency to transmit their signals. Right. So when I talk about the applications again, the mobile satellite communications will is defining the communication that happens between a mobile device and a satellite. So mobile satellite services, mobile satellite services, which we call as MSS, is targeted to provide satellite communication to mobile devices. So this is targeted to provide like connectivity to mobile device, right? Provide the communication to mobile devices. Provide the connectivity to the mobile devices, right? Provide the connectivity to the mobile devices. So in here, the mobile connectivity or the mobile satellite services mean that the device which is mobile is a like a smartphone or a laptop, tablet, and likewise. So mobile satellite services are provided for devices which are in locations such as like I mean in the air or in the ocean, where we cannot reach through the fiber cables, right? So mobile satellite services are provided for devices um, which are located in remote locations in the earth. It could be devices which are in the air, in the atmosphere. I mean in the upper layers of the atmosphere, or it could be devices which are located in the ocean or in the sea space areas, right? Which are unconnected or not connected to the other places in the earth. So in that location, in that scenario, we will have these satellites transmitting using the L band frequency to those devices which needs connection. Right, so that service provided by the satellite is known as MSS, Mobile Satellite Services. And then we have the S band, and S band is used for again mobile satellite services plus the to facilitate communications required for the NASA and required for deep space search, right? And then thirdly, we use a C band, which is defined as the band within the frequency 4 to 8 gigahertz for fixed satellite services. So what do we mean by the fixed satellite services? Fixed satellite services means like if we have two fixed locations, between which we want to communicate, as given in this scenario, we will use the fixed, satellite services, because we know exactly where the transmitting station is and the receiving station is. The location of the ground stations do not change over time. So for communications that happen between two fixed locations, we call as fixed satellite services, right? Fixed satellite services are for a communication that happens between fixed locations in the earth, right? And then we have the military based applications, or military based communications that are done using X band, and it will have a frequency from 8 to 12. And then we have the Ku band, where the Ku band frequencies are used for TV and radio broadcast communications, right? So if we want to send our TV signal from one distant location to another distant location, we can send the signal to the satellite. The satellite will transmit it to the distant satellite, and we'll be able to reach a distant location using that communication. So basically, the TV stations and the radio stations will be using the Ku band to communicate with the satellites. And then we have the fixed satellite services again in the K band, right? So we sometimes have the different situations, like in here with the fixed satellite services in the K band. The difference is, like, we have voice data communications happening uh, for points in fixed locations on the earth, right? So differences can be seen in different frequency bands, and the frequency is used for specific use cases. And then we have finally the K band, which is used for broadcast satellite services. So that broadcast satellite services are also used for broadcasting services. And the broadcasting services are used to like send the signal using a very high frequency in this K band. So that is basically regarding the frequency bands and the applications, right? I hope it is clear to you. If you have any questions, you can ask. Then we have the satellite orbits, about which I would like also to discuss. Satellite orbits, right? So in here, in this simulation, we can see satellites orbiting in specific orbits. And in here, actually, we can see the satellites are placed at a certain distance from the Earth. So based on the distance uh, that the satellite is placed with respect to the Earth's surface, there are basically three orbits that are defined. Mainly, there are three orbits that are defined, right? So those three orbits are basically the uh, geostationary Earth orbit, geostationary Earth orbit, geostationary Earth orbit. Next, we have the um, like medium Earth orbit, medium Earth orbit, and the low Earth orbit, right? Low Earth orbit. So uh, these all these orbits are used for different applications. However, like currently, Leo Earth orbit or low Earth orbits, Leo satellites, right? We call these satellites which are using this Leo orbit, Leo satellites, and those Leo satellites are getting very popular. We also have this medium Earth orbit, and we also have the geo or the geo satellites, geo Earth orbit or geostationary Earth orbit satellites. So let's discuss about these satellites in detail. Um, I think before talking about those, like satellite situations, orbits, let's discuss a little bit about the MATLAB simulations that we uh, we can do via MATLAB as well, right? So let me try to show you the simulation that we will be discussing. Right. Last week we discussed about the um, modeling of satellite scenario using MATLAB. So I will, you know, we will start discussing about that MATLAB simulation first, and then I will discuss about new MATLAB simulations. So in the last class, we discussed about this MATLAB simulation and how we can define this simulation scenario using certain parameters. So we discussed about setting the start time, stop time of our simulation, and the sample time. So we can define these dates and times as we want, and we can do the simulation between those two time duration time points. And then we have sample time where we define the sample time to be a value which is in seconds. So each 60 seconds, the sample data will be generated by the simulation about the scenario we are considering, and it will plot the satellite scenario. And we also have the commands to generate a satellite scenario by using the function called satellite scenario. Apart from that, we can then define the satellite like constellation using like a TLE format file. We will discuss about that format as well in a later instance. Then using this predefined constellation pattern that we have defined, we can you can define a satellite object using this command satellite, and inside brackets we can put the satellite scenario that we generated earlier, and then comma we can define where the satellites are located and all those features related to satellites using this TLD file. And then we will show the satellite constellation using visuals in the MATLAB, and then we will have ground track of the satellite orbits. So we saw in our simulations that like all the time we can observe the ground track of the satellite moving in the orbit. So so most of the time if the satellite is moving, we can see the ground orbit or the ground path of the satellite as well. So I think I will run this code, and this it will generate this visual of the scenario. We generate the visual of the scenario, and it will show that the satellites are moving, and the ground track of the satellites. The ground track of the satellites we can observe using yellow lines, right? We can observe the ground track of the satellites. So I think we can observe the satellite moving, and we can observe the path of the satellite using this yellow line, and this purple line is the line where we are predicting the ground track of the satellite. So that predicted line is known as the lead time, or the time up to which we are predicting the satellite ground track, right, is known as the lead time. So the lead time, we can see that it has been set to 1200 seconds. That means 20 minutes. So of about 20 minutes, we can make a prediction of the ground track using this command. And then we can also check about the orbital elements of the satellite. That means like the different features of the satellite orbit and the satellite we can define using this orbital elements function, right? So the parameters such as the mean motion or the velocity of the satellite is given, eccentricity, inclination, likewise, different parameters are given using this, are included in this orbital elements structure. Then we also can change, if we want, we can change the epoch, the time of the time of initiation of taking measurements. We can set to preferred value, such as 24th of October 2023, which is today, right? So we can define the epoch of the orbital element using by defining the element dot the epoch equals the time or the date and time that we want to start the simulation on, right? And then afterwards we can also continue to do that for the other satellites as well. So what we do here is basically we are setting the time at which the simulation should start collecting the data about the environment. And so likewise it will go on and it will collect the data regarding the environment. Apart from that, right, we can we can also obtain the position of the satellites at a certain time of our preference. So we can do it using these, commands. We can return the latitude, longitude, altitude of the first satellite on the time that we define, right? So although in here it is mentioned as 2nd of June 2020, we have given the date and the time to a date on the October 17th. And at that time, the position of that satellite will be given using this function called states. So likewise, there are some commands that you can go through, and we can define the locations of our ground stations using latitudes and longitude values, and we can define the names of the ground stations as we want. And then once we have defined the locations of the ground stations, we can observe the ground stations being there in the visual simulation. Apart from that, we can also use the function called AER, and inside we can include the parameters related to the ground station and the satellite location and the time, and then we can obtain the angle and the elevation angle of the satellite with respect to the ground station, right? So we can obtain angles with respect to the ground station about the satellite using this function. So likewise, we can go ahead and we can use different functions to obtain the required parameters from this satellite simulation. So this satellite simulation shows the existence of ground stations, satellites, the ground track, and so on. So likewise, we can do MATLAB simulations of the satellite scenario. So there's another example that we'll be considering today, which is like the communication that is happening between two distant points across two satellites. So across two satellites. So basically the example that we looked at earlier, we will discuss now. So this is the example that we are considering here. So in here that we are doing the communication between the Indian subcontinent and then the Australian continent, and then we are connecting our signal with the satellite up in the orbit. The satellite is sending that signal to this satellite, which is out in the uh, in another orbit, right? So we first send a signal from the subcontinent, Indian subcontinent, to the satellite out in the orbit, and in from the orbit, the signal will be sent to a satellite which is in another orbit, and it will receive that signal from the first satellite, and this data will be transmitted to the ground station in Australia, right? So this is the simulation that we want to create. So when we want to create it, we can use the sample code that is given in the MathWorks website as well. And in here you can determine the start time, stop time, sample time, and satellite scenario just as the previous simulation. And then we can set where the satellite should be placed, and any other parameters related to the satellite's position, inclination, angle likewise. Then we have the ability to uh, add gimbals to the satellites. So the function of these gimbals are basically to add cameras and sensors to the satellite, right? So the satellite will be having these gimbals, and it will be able to collect the images of the Earth. And also the cameras have a certain angle at which it is capturing the images. So using this controlling unit, we can control the angle at which these cameras are working in this component. So we can define in this MATLAB simulation where this gimbal component should be placed, and then where the camera angle should be in place. So we can decide in what direction the camera should be in place. So we can add transmitters and receivers to the gimbals as well, and we can give the parameters of those transmitter and receiver in these sections. So after configuring all these components related to the gimbal and the like ground stations, satellite, then we are able to connect the satellite and I mean like generate the communication, right? So anyway, like the sample code is available in MathWorks. You can run it and you can check the performance of the simulation, and then you can like check how you can customize it for your own application scenario that is considered, right? So this is the final output of the simulation. So basically we can set up ground stations at the location that we want, and then we can set up satellites in certain like orbits, and we can define like where the satellite should be placed, and then we can define the angles of the satellites, the angle of the gimbal that is placed inside these satellites to obtain pictures and information regarding the Earth and the space. And we can go ahead with the receiving and transmission of the data via the two satellites, and we can connect using the satellite links. We can connect 2 points which are very distant apart, right? So that is basically regarding the link generation using MATLAB simulations, right? So basically I think like Matlab provides a really good platform to test the satellite communication designs and check the output performance, right? Apart from that, there is also another app which is called Satellite Link Analyzer, satellite satellite link budget analyzer, which is useful for us to obtain the link budget calculation in satellite communications. So we will talk about the link budget analysis also. However, like this tool or this app is helpful for us to calculate the link budget of the satellite communication. So we are calculating this link budget, and we are designing the satellite link such that our our performance is maintained. So once we give inputs to our satellite simulation in this I mean once we give inputs to this application, then we can obtain the uh, correct link parameters from this software, and we can design the link as defined uh, by the software, and we can verify the performance of the design as well, right? Anyway, so Matlab provides this link budget analyzer app as well. So I believe that since we have covered like a somewhat like a um, somewhat um uh, uh, like a good amount of content, we will end the class as of now, and then we will continue from the rest of the section from the next class onwards. So I hope that you understood what I have explained during the lecture. If you have any questions, you can let me know. You can contact me through my email, and I will answer your questions. So for now, thank you so much for joining in for the today's class. So I will end the lecture now.